Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let me introduce the next oral presentations, which is about the learning theory and algorithm for forecasting non-stationary time series. And the talk will be given by the Vitaly Kuznetsov in the Curran Institute in NYU.
Thank you for the introduction. Let me just set up my slides here.
Let's see.
Thank you again for the introduction. It is my great pleasure to present my joint work with Mary Mori on learning theory and algorithms for time series prediction. So let me start by telling you what I mean by time series prediction, and I will do that by contrasting this setting with the standard learning scenario. In the standard learning scenario, the learner receives a labeled sample, which is assumed to be drawn IID from some unknown distribution. And then the goal is to predict the labels Y's on unseen examples X's, which are again assumed to be drawn IID from the same unknown distribution. Now, in time series prediction, the learner now receives a realization of a stochastic process, x1, x2, up to xt, and the goal of the learner is to forecast the next value of the stochastic process, xt plus 1. And of course, in general, there might be dependencies between these random variables, and they may even have different distributions. So in general, IID assumption may not be valid. So how can we analyze this setting, right? How can we derive algorithms for forecasting time series in the absence of this assumption? Well, the standard way to proceed is to assume that the underlying stochastic process is stationary or suitably mixing. Stationarity simply means that the distribution of your stochastic process does not change with time. And mixing is a slightly more technical condition, but roughly speaking, it means that the dependency of your stochastic process on its past decays with time. So these two assumptions may seem rather natural, at least at the first sight. And indeed, they have been widely adopted in machine learning and statistics literature. Right? But are these the right assumptions? Let me criticize a little bit these two notions. So first of all, both of these notions, stationarity and mixing, they consider only the distribution of the underlying stochastic process, and they actually ignore other key components of the learning problem, such as the loss function and the hypothesis set. These assumptions are not testable except for some trivial cases. And moreover, in fact, it is often the case that these assumptions are actually not valid. And let us look at a very simple example first. Suppose I flip a fair coin once and for all, and if I see heads, then my stochastic process traces out a sine curve. And if I see tails, then my stochastic process will trace out a cosine curve. It's actually easy to see that this stochastic process is not going to be stationary simply by observing that the mean of this stochastic process is not constant. And it is also fairly easy to see that this stochastic process is not mixing. And you can do that by recognizing that the past of this stochastic process completely determines its future. So existing theory sort of suggests me that learning should not be possible in this case. Yet, learning or forecasting in this setting is trivial, right? I just told you that the past of the stochastic process completely determines its future. Okay, so this is just a simple example, but there are many other real-world examples of stochastic processes that are non-stationary and non-mixing. So, for instance, so-called long memory or fractional ARIMA models may not be mixing just by their nature. Markov chains, most widely used stochastic process in applications, is not going to be stationary unless it is started in an equilibrium distribution. In fact, most of the stochastic processes with a trend or seasonal component are not stationary. So it is natural to ask whether it is even possible to learn with these stochastic processes. So, and this is precisely the question that I'm going to focus on in this talk. So I'll start by giving you some definitions and tools that we're going to need. And then I will discuss learning theory for time series prediction. And I will use this theory then to present some algorithmic solutions for this problem. Okay, so let us start by examining the goal of the learner in time series prediction a little more formally. In the standard learning scenario with IID data, when we fix the hypothesis set and the loss function, the goal of the learner is to find the hypothesis with the smallest possible generalization error. That is the smallest possible expected loss on unseen data. However, when it comes to time series prediction, we're actually facing our first challenge because it is not immediately clear what the goal of the learner should be in this setting. So one natural option is to seek a hypothesis that has the smallest expected loss in the near future, conditioned on the whole history that we have observed. And this intuition is captured by so-called path-dependent generalization error that you see at the bottom of this slide. So how can we analyze this path-dependent error, right? Because I told you that we don't want to rely on assumptions such as stationarity and mixing. So what are the tools that we can use for this analysis? Well, there are two key ingredients that we will require for this analysis. And the first key ingredient that we're going to need is the notion of so-called expected sequential covering numbers. So if you're familiar with covering numbers from classical learning theories, then you could think of these as natural extensions of classical notions to the setting of sequential data. The second major ingredient that we will need is the notion of discrepancy measure, which will help us to quantify the divergence between the distribution of the future that we are trying to predict and the distribution of the sample that we're observing. In this talk, I will focus on discrepancy measure due to the time limitation, but I would like to emphasize that covering numbers are also a key component of this theory. Okay, so what exactly is this discrepancy measure? It is defined to be the maximal possible difference between the generalization error of the hypothesis in the near future and its generalization error on the sample that we're observing. And one can think of this discrepancy as a natural measure of non-stationarity of the stochastic process. For instance, if the sequence of random variables that I was observing was actually IID, then the discrepancy would be exactly 0. More interestingly, if we're dealing with a large class of weakly stationary stochastic processes with a squared loss and linear hypothesis, then the discrepancy is exactly 0 again. And this actually highlights an important property of discrepancy, that it captures not only the distribution of the stochastic process, but also the loss function and the hypothesis set that is being used. Discrepancy is a new notion, but it is closely related to other generalized Kolmogorov-Smirnov distances that have been previously considered in domain adaptation and drifting settings. It has a number of other additional useful properties, such as it admits upper bounds in terms of familiar distances between distributions, such as L1 distance, relative entropy, mixing coefficients, and so on. But most importantly, at least in my view, under some additional mild assumptions, discrepancy can be estimated from data. Okay, I think now we have all the tools that we need to present our learning guarantees, and what we show is that with high probability, uniformly over a hypothesis set, path-dependent generalization error is going to be bounded by the following three terms. The familiar empirical error on the sample, discrepancy that I have just mentioned, and a term that captures the complexity of the hypothesis set that is being used. And this term is expressed in terms of the expected sequential covering numbers that I have mentioned earlier. Now, since we have non-stationarity in our data, it may not make sense to value the errors of a hypothesis on a different sample points in the same way. And in fact, it may make more sense to emphasize certain sample points more than the other sample points, right? And it turns out that actually we can replace the uniform weights 1 over t in this bound by an arbitrary probability distribution Q over the sample points, and the exact result is on this slide. This is going to be important for us later on when we derive our algorithmic solutions. But before we get to talk about algorithmic solutions, I would also like to talk about discrepancy estimation, because it's also very important for algorithms. The bad news is that, in general, estimating discrepancy directly is hopeless. This is simply because, as you may remember, discrepancy depends on the distribution of the future that we're trying to predict, and we never receive any samples from the distribution of the future. But we can upper bound discrepancy by delta 1 and delta 2, where delta 1 is the discrepancy between the recent history of the stochastic process and the whole sample, and delta 2 is the discrepancy between this recent history and the future that we're trying to predict. Now, delta 1, as we'll see on the next slide, can be estimated from the data, and delta 2 is assumed to be small. This turns out to be actually a rather mild assumption, because one can show that even in the case of drifting, which is a subcase of the problem that we're considering here, this delta 2 enters a lower bound on the generalization error, making the learning hard if this quantity delta 2 is large. Okay, so our final learning guarantee is presented on this slide, and the difference with the previous result is that we replace discrepancy by two terms, delta 2 that I have just explained to you, and empirical discrepancy delta tilde. And this empirical discrepancy is defined to be the maximal possible difference between the error on the recent history and the Q-weighted empirical error on the whole sample. These are the first learning guarantees for non-stationary, non-mixing processes, and these guarantees are data dependent. And it is important that these guarantees are data dependent because it allows us to derive algorithms for time series prediction by simply directly optimizing this upper bound. So in particular, we propose to optimize the following objective. The objective consists of the following four terms. The first term is a Q-weighted empirical L2 loss. The second term is the Q-weighted empirical discrepancy that we have discussed. And the last two terms are regularization terms. The first regularization term controls the complexity of the linear hypothesis that we're using, and the last term controls the deviation of the distribution Q from the uniform distribution. Now, the unfortunate property of this formulation is that since the optimization is joint over Q and W, this optimization problem is not convex. But it turns out that using duality, change of variables, and slightly restricting the domain of the optimization, we can arrive at an alternative formulation, which is going to be convex, and that's a nice property. The final ingredient that we need for our algorithm is computation of discrepancy, because as I have mentioned to you, discrepancy is used as an input to our algorithm. Right? And let me tell you how to do that. So here is again the definition of empirical discrepancy at the top of this slide. And as you can see that in general, finding this discrepancy is a non-convex optimization problem. But if the loss function that you're working with is actually a convex loss function, then you realize that this optimization problem is a difference of convex functions optimization problem. And one can use a DC algorithm, for instance, DC algorithm of tau and an to solve this optimization problem. Moreover, if the loss function is the squared loss, as it is the case for us, DC algorithm can be shown to recover the global solution to this optimization problem, which is nice again since we can accurately find the inputs to our algorithm. Okay, I'll conclude. In summary, we present the first learning guarantees for learning with non-stationary, non-mixing processes. Our guarantees are data dependent, and they're expressed in terms of a discrepancy measure that can be estimated from data. And we use this theory to provide some algorithmic solutions for forecasting non-stationary time series. Now, in this talk, I've focused mainly on the theory due to the time constraints, but we have implemented these algorithms and we have some favorable preliminary experimental results for this, and I would be happy to talk about this at the poster. So that concludes my presentation. Thank you for your attention. And I would also like to use this opportunity to invite all of you to a time series workshop that we're co-organizing this Friday. Thank you.
Okay, so we can take a few questions, but in the meantime, I would like to ask our spotlight presenters to start up lining up here. So, any questions? Then let me ask you one question, actually. And the discrepancy measure you introduced, is something related to the Rademacher complexity, right?
Well, it's not directly related to Rademacher complexity, but it's similar in the sense that it captures not only the distribution of the process, but also the loss function and the hypothesis set. So it fully captures all the relevant notions to the learning problem.
Okay. Yes, one question.
Hi, thanks. Very interesting. Question about delta 2, the piece of the discrepancy that needs to be small for learning to be possible. What can we do with the available data to check that, or try to look at the rate at which in the historical past of the sequence it in fact wasn't small? I mean,
well,
are there ideas along those lines?
You can sort of look at delta 1, and if delta 1 is actually small, then you could expect that hopefully delta 2 is small. But I mean, in the worst, very adversarial case, right? If I give you one stochastic process and then I ask you to predict something completely irrelevant, then the quantity like that should enter the bound, right? And this is exactly delta 2.
Okay, so you'd need to impose some kind of idea of regularity in order to say something.
Yeah, I mean, if you're trying to, if you see irrelevant sample, then you shouldn't be able to predict, right?
Yeah, thanks.
Okay.
So, very interesting work. So my question is that whether discrepancy and sequential covering enough to characterize what is learnable. Like, in other words, is it possible that there is a learnable problem, but discrepancy or sequential covering, either of them are infinite?
So you're essentially asking for the lower bounds, right?
Yes.
So yeah, in certain special cases, for instance, just for sequences, right, in online learning, right, the sequential covering numbers completely characterize learning in that setting. And discrepancy, as I said, enters a lower bound even in special cases for this scenario, like drifting. Generalization error can be lower bounded in terms of the discrepancies. So yes, if either of those quantities are infinite, then you wouldn't be able to learn.
All right, okay, so let's thank the speaker again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.